so now backwards to the sun. We're going to hop around a little bit because we avoided chapter 3, 4, and 5 in the textbook would be like physics, and physics, so I think everybody would die. So this is the first time, and we've kind of hinted at it a little bit with some infrared images of the gas giant planets and some discussion about ultraviolet radiation. But now when we talk about the sun, it's really time to start talking about spectra. And we'll do a little bit today and a lot on Wednesday with a lot of demos. So we'll black out the entire classroom and look at some quantum mechanics. Then our star as a template for all stars. So next week we finally start getting into probably what you expected from intro astronomy, is talking a lot about stars. So this is sun, it's our star. It is all but 14 or 15 thousandths of the mass of the entire solar system. It's the source of all of the energy at the surface of Earth, the source of all of our, trophic cascade, our food chain. All the light that you see in the solar system, at least visible light, is predominantly sunlight that's reflected. And from a scientific standpoint, it's going to be our model for studying other stars. And a lot of this has been done just as like some kind of historical reminders, is disregarding the 1,500 years of silliness, at least in the Mediterranean world, is people actually had a lot figured out in ancient times. So some of the ancients, like 300 BC, used techniques of like, well, I know that I know the moon is this far away because it appears to be, this is the radius of Earth as cast by the shadow in an eclipse, and this is the radius of the sun. I can compare them and say that, well, the moon's got to be, this fraction of the Earth's radius, therefore it looks this big, so it's got to be that far away. That number was actually figured out pretty precisely, is that the moon is about 60 times farther away than the Earth's radius. You can just tell kind of by looking at that shadow and knowing how big the moon appears. And then you can do some geometry. You can figure out the sun is so far away based on looking at, what angle the sun appears at when the moon is at half phase. And the first calculation for that was actually really wrong. And Aristophanes got that the sun was like 108 times larger than 7 times larger than the Earth. We now know that it's about 108, and that was figured out a little bit later. So by the time Kepler came around, his third law said that there seemed to be some mysterious order in how fast you orbit versus how far you are away from the sun, and the sun is at the center. So this would be the average distance, because things are a little bit elliptical. And this straight line tells you what, now that you guys are halfway through exercise 5, the mass that I would get by looking at the distance and the distance and the period of Mars and the distance and the period of Jupiter is what mass? Whose mass? Yeah, so it's the mass of the thing that's pulling everything around, not the thing that's being pulled. So if I were to take these period times and these distances, average distances, actually sitting right here, I have 9 independent measurements of the sun's mass. And this you could do, in 1680. And so you do this and you actually get the mass of the sun, and the mass of the sun is known to people who wore powdered wigs was 2 times 10 to the 30th kilograms. So that's really, really, really big and massive. So that's actually fairly incredible to think about. And then the real question remaining, because that's kind of just mechanics physics, is what's going on with the light? So this is the body that shines. And when you look at the moon, for instance, this phase of the moon, where's the sun? The moon is in this configuration. It's over there, right? Because you're seeing reflected sunlight. Where's the sun? All right, where's the sun? And aside from the Pythagoreans who had this bizarre idea about like the great hearth of the universe, people knew this. So this is an old question. So what's making the sun produce light? And imagine that you live in the 3rd century BC. What's the one and only thing that you know that produces heat and light? Fire. So for millennia, people appealed to the obvious theory that the sun is producing heat and light by burning stuff. And this slowly became kind of untenable. So once you start, it's actually, this question is totally connected to the to geology, because as the geologists and the biologists started getting back into deep time and figuring out how old the Earth was, all of these theories started becoming like impossible to hold. So, if you really just find something that burns for a long time, like coal on planet Earth, you can do the calculation. Even with 2 times 10 to the 30th kilograms of coal, you get a few thousand years of burning. So coal actually doesn't have a lot of energy in it. So, okay, fine, it's oil or some magic cosmic oil. Newton kind of would scrap that theory because his idea of universality says that no, there's no magic stuff out in the cosmos. It's got to be related to physics that you could see on Earth or chemistry that you see on Earth. So the next slightly less obvious theory came along in the middle of the 19th century. And the reason to talk about it in a bit of detail is not that it has anything to do with why the sun is shining now. It's incorrect. For a current explanation of why we have a bright sun, but it's correct physics, and it shows up a lot at other stages of solar life, and it shows up a lot in just clouds in the solar system, in the universe. So very, very sneaky. So the 19th century, steam engines, things like that, this was kind of the birth of thermodynamics. And so you guys, Kelvin and Helmholtz, they didn't collaborate, but they contributed to this idea that it's gravitational contraction. And the basic idea is, let's say that your car tire is low or your bike tire, and you take a pump and you pump it up. So you squeeze all these molecules of air, and then you feel the tube of the bike pump. What do you think is going to happen? Even if it's somewhat subtle, think it's going to cool down or other thing? Yeah, heat up, right? So if you literally mechanically bash molecules into other molecules, you're heating them up. And so the idea was that gravity is doing this. So slowly, almost imperceptibly, over the course of its lifetime, the sun is producing heat and therefore light because it's slowly shrinking, was what they thought. And gravity squeezes this thing into a ball, heats up the sun, heat turns into light, and if you came back like a million years later, the sun would be a little bit smaller, and then a little bit smaller still, and a little bit smaller still, and at the end of it, you would get this very inert ball of gas, like a super Jupiter or something like that. Their calculation, which turned out to be kind of correct, the physics was right, was that you get 25 million years of energy out of this. Now, this is in 1840. So there were 2 groups of people, the physicists who think they're real scientists, and they said, look, we equationed it out. The sun has got 25 million years of energy. I also equationed it out. If you start the Earth with a molten bowl of iron, I've done calculations based on hot iron balls from the cannonball factory, and the current temperature of the Earth says that the current age of the Earth is also 20 million. So these numbers are in complete agreement. They're both completely wrong. So all the geologists are like, you can't do this. You can't have 25 million years to erode a valley in Scotland or Norway. That's nonsense. So you can't even erode a single lump of granite in 25 million years. So I don't believe this number. And then Darwin came along and he said, actually, I'm going to push you back to hundreds of millions of years because you can't turn single-celled organisms into dolphins in 25 million. There's no way to do it. So this idea from other disciplines of deep time, and the physicists were wrong. I hate to admit it. They were really wrong. Okay. But this is actually a correct mechanism for making heat and light. You can absolutely do this. And before the correct thing that actually makes our sun shine currently kicks in, this totally happens in pre-stars, protostars. And this totally happens in other things. In fact, that's why Jupiter is a little bit hotter than Earth is, sort of anomalously hotter. It's because it's still gravitationally contracting a bit. So why does the sun actually shine? Yeah, the totally obvious theory, E equals mc squared. And this is a lot of energy. So the idea, and it's actually weird because this E equals mc squared thing, it's this equation that's totally iconic with genius. It's so you want to show that somebody's a bright person, you put it over their head in a word bubble or something, right? Does anybody ever kind of piece through why that is? Because Einstein said it. I know. So, well, for one thing, it's something that's implied by relativity, but it also is like a stroke of insight that, in fact, Einstein himself, as far as I know, didn't make, is that to say that two things are equal in an equation does not mean that you can kind of convert in between them. So, for example, if you go to KFC and get a bucket of chicken for $8, say bucket of chicken is $8, does that lead you to believe that you could put $8 in a box and shake it up and then open it and a bucket of fried chicken would appear? Yeah, very convenient, wouldn't it? It's the fact that this is not like a formal equivalence, is that you can actually convert mass into energy, is the really important insight, which unfortunately had some really terrible first applications. So it is literally true that you can turn mass into pure energy at the conversion rate of the speed of light squared. The speed of light is very big, so the speed of light squared is very big. And to put this in perspective, this is not the one, but the bomb that the American military dropped on Japan, each one of those, it basically lost half a gram of mass. So imagine cutting a paperclip in half. That's how much mass was evaporated, and that annihilated a city. So this is good. Imagine if you had to burn, how much coal would you have to burn down a city? Quite a lot. How much gravitational contraction would you have to destroy a city? I don't know. If you take up if you were able to do this and you were able to find forget about a broken watch in the ocean, if you were to find all the bits of the Hiroshima bomb and piece them together and weigh them after the explosion, half a paperclip less. So that was converted into pure energy. Yeah. So the important part is that this is enough. And this was realized in 1940s. So in fact, decades after, as a mechanism for the sun shining, it was realized decades after this kind of formal E equals mc squared thing, which again, like everything else, just gets stapled over Einstein's head like he thought of it all. Don't get me wrong, he definitely deserves all the credit that he gets, but this actually really isn't him. In fact, the story goes, if you want lurid science stories, this isn't really a super lurid one, is somebody figured this out, so they're like, oh my God, the math works out. This is a total explanation for how much energy the sun can have. I predict that the sun would live on total for something like 10 billion years. And this is in complete agreement with biological timescales, which by 1940 are reaching back into billions of years. And so this is the one and only person on Earth. Now imagine, if you're a scientist or a chemist, this is like haunting you. Every day this ball of light comes up in the sky and says, you don't know how I work, right? So it's terrible. So this person figures it out, first person to do so, and knows he's correct. And he's so excited that he goes out to a party, and it's like rural England because he was at Cambridge, so he's drinking and driving, and people have to basically hold him down at a party and say, tell us why the sun shines in case you wrap your car around a tree. So I was pretty excited. But this is it, and never forget it. It's E equals mc squared, and c is a huge number. So small mass, big energy. Any questions about that? It's not an obvious thing. So the real question is how? And it's easy because it's a word bubble over Einstein's head to just say, of course, stroke of genius, Einstein did it, I'll never understand it, let's move on. But this is, so I really don't have a complete explanation, but I can at least peel back one layer of the weirdness, is that it turns out that if you follow a proton on a journey as it goes so protons were made at the beginning of the Big Bang, they were made by themselves, they weren't made in, as a constituent in carbon or gold or something like that, is that there's just a proton, and a proton has a mass. You can weigh a proton. And it turns out the real question and the real quirk of nature is that if the proton is in hydrogen, which is to say it's all by itself, it has some mass. If it's in deuterium, which is hydrogen with a neutron, it has a different mass. If it's in helium, it's two protons, two neutrons, it's got a different mass. If it's in iron, it's got a different mass. So as protons go and hang out in different nuclei, one or another, it actually has a different mass. So it turns out that depending on what element you're in, you have a different amount of mass per nucleon. So all of a sudden, you somehow convince a hydrogen to hang out with a proton to hang out with a neutron. You go from two things with this mass to two things with that mass each. That mass is lost and released as energy. So basically what I'm saying is this is the mass per nucleon chart, and it's lowest mass per nucleon at iron. So it goes down, 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 down to get iron, and then back up to exotic things past uranium like californium. Things get really unstable there. So if I take small elements and I smush them together and make bigger atoms with larger number of protons and neutrons in them, what happens to my overall mass? So in this case, as I'm small to large, as long as I'm below iron, more and more stuff, less and less mass. What's that called? So I take two small atoms and I smush them together and create one larger atom. That is fusion. And it turns out the quirk of nature says that if you do that, if you take, two protons, two neutrons, and you smush them together and you make one helium out of them, just take the same two things and smash them together, all of a sudden in this new configuration, they just say, hey, I've got less mass. I'll release a bunch of energy. Okay. And then otherwise, here, this has a larger mass per nucleon than iron does. So if I take one uranium-238 atom, and this is the first, again, kind of very sad application of nuclear devices, is that if I take one U-238 or 235 and I split it apart, break it up into two individual atoms, so instead of one U-238, I get two things which are less massive. They also have less mass per nucleon. So energy is also released. So what's that process? Fission. So this is fission and fusion. And it turns out that if you're going from smaller to bigger and you're below iron, you release energy. Less mass, energy is released. And if you go from larger to smaller by splitting stuff apart, you release energy too. Why exactly a proton would care who it's hanging out with to have a different mass is, that's actually pretty, kind of far out physics to do with many body effects and renormalization of things. But this is it. Okay, so if you're small nucleus and you smush things together, you can release energy by going towards iron. If you're a large thing, you can break apart and release energy by going towards iron. So iron is like the nadir. Iron has the lowest mass per nucleon. So you always have to put energy into iron to turn it into anything else. Any questions about that? Okay, we'll get back into some of it and realize that there's something really weird going on here. But the short story is that I have 2 times 10 to the 30th kilograms of material all bearing down on something. I can convince these protons, which otherwise would hate hanging out next to each other, right? So positively charged, they would love to repel. If I put them inside this disturbingly large amount of mass, I can actually squish them so much that they will, in fact, turn into deuterium, a proton and a neutron, and then turn into helium. And at some point along the way, something really weird happens that we'll have to talk about later, is that 2 of these protons just decide that they're ready for nucleon reassignment and become neutrons instead of protons. But the important part is 4 protons used to hang out by themselves, turn into 1 helium, less mass per nucleon, energy is released. Ta-da, the sun shines. And we'll get back into some of the details of this, namely what's going on with the protons magically turning into neutrons. Okay. That energy is released in the form of, for one of these reactions, 2 gamma rays. So 2 really, really, really high energy evil bits of light. So gamma rays are what happens if you have some nuclear waste and it's irradiating you. Gamma rays are the thing that turn you into a Marvel superhero. So evil. Okay. It's not true. Okay. So this is all happening at the core of the sun. So basically you could think about everything else, so all of these outer layers, as basically the weight required to make the fusion occur at the center. So the entire role of this stuff is to be bearing down on the center and producing fusion. So this actually is, so now that maybe you're kind of like scared that you live in a, 1 AU, which really doesn't seem like a very large distance now because you have 10 to the 30th kilograms of thermonuclear bomb going off in your backyard. It would be nice to know if this is stable. And yes, so there are two forces, and it turns out they balance, and they balance really nice. So you have gravity trying to crush the star. Maybe gravity will win, maybe it won't. And then you have this pressure from the thermonuclear bomb constantly going off, eating hundreds of tons of material in a second, pressing the thing outwards. And then the gamma rays that are emitted actually interact with this material, bounce around, and over the course of about 1 million years, they actually turn into much friendlier types of light. But that's kind of we'll get into the details of it in a minute, but that's really kind of it. There's like a nuclear fusion candy core, and then everything else has the role of squishing it to make sure that that fusion happens and, in a sense, doesn't really care about us, but insulating us from the gamma rays. Any questions about that? Okay. So this is nice, and this is one of the gifts that nature has given the stability of, for all the bad things that happen on and impediments for maybe making like life on planets, if you care about that sort of thing. This is not one of them. This is very, very helpful, is that this is a self-regulating process. There's kind of a complicated depiction of it in a figure in your book. It's called the solar thermostat. But what it really means is that if you start letting one of these two forces run away, the other one will intervene and fix it. So if you imagine that for some reason or another, like the thermonuclear bomb starts going off faster and there's more fusion in the core, what's going to start winning? Pressure. So the pressure starts winning. What'll happen to the star itself? It'll expand and puff up, and then actually, because it's bigger, more energy will be released from the star. So if you make this thing bigger, it'll actually radiate more energy and it'll cool down. If it cools down, what's going to happen to the pressure? It's going to go down. Otherwise, you could think if the radius of something increases, what happens to the gravity, like the surface gravity at some point? So the bigger the radius, the smaller the gravity. So everything about that wants to slow fusion down. If fusion increases, gravity will compensate and say, I don't think so. Okay, so let's say gravity starts winning. So if gravity starts winning and this thing starts imploding, that would be terrible too if our star starts imploding. What's going to happen to the rate of fusion? Well, I start crushing more protons and more neutrons together. So if gravity starts winning, fusion kicks up, and fusion pushes back the other way. So this is a stable process. Wonderfully stable. It's really nicely stable. There's no day where you look at the sun and say, like, boy, the sun's extra bright today. That's scary. If you do, it's because of the atmosphere, and also don't look at the sun. So people call this the solar thermostat, and it does make sure that, puts out the same amount of power on a day-by-day basis. Okay. So now, kind of quickly, we'll just take a tour of it's kind of what we did with terrestrial planets, like cut the sun in half and then talk about the parts. And there's some, you can like tease out all the bits of the solar atmosphere and stuff like that, but it's actually not really that important. We'll just say that there's the photosphere and corona for you guys. So the core, that is the absolute center of the star. The core is where fusion happens. The core is, for our star at least, 16 million degrees Kelvin, so that's pretty big. You can ask how on earth people know that. The answer is detailed calculations having to do with thermonuclear fusion. The density, now that people are about halfway through exercise 5, this number might start being meaningful. Earth, which is basically a giant lump of nickel and iron, is about 5.5 grams per centimeter cubed. The density in this 16 million degree Kelvin star core is about 160 grams per centimeter cubed. So that's holds something about this big, and it's it's about the weight of, 160 grams is probably like, like the lightest weight at a, no, it's not even enough. About this much brass maybe, so reasonable amount of brass. So very, very heavy, so about 10 times lead. So after that, there's a portion of the star called the radiation zone, where the entire mechanics of what's going on in the radiation zone are these evil, high intensity, high energy photons, parcels of light, just trying to fight their way through and interacting with not quite as dense and as hot as the core, but pretty hot and dense matter. So this is actually the majority of the sun. It's about 85% or so the mass. And the real role of the radiation zone is it's like radiation trying to escape, fighting its way out. But in fact, the stuff is so dense that, and it's completely opaque, right? So it's not transparent, is that light will travel for a very short amount of time or distance. It'll bounce into something, get re-emitted, re-emitted, re-emitted. And as it kind of random walks its way through this, it actually takes about 1 million years. So you make a gamma ray by fusion here. About 1 million years later, on average, it'll fight its way out to the edge of the radiation zone. So that's good, because after all of those interactions, it turns from the evil, evil gamma ray into like some normal thermalized set of very longer and less nasty wavelengths of light. So that is the idea behind it. But imagine, yeah, I know, like this many interactions would probably happen in a trillionth of a meter or something like that. So this is not like, the thing doesn't bounce 4 times and get out. So this is just an idea of what the random walk of a single photon is. Yeah, it's the packet of light interacting with some matter. It's not fair to call them atoms because they're not neutral. So it would be a free electron, which is not hanging out in an atom, or a free proton or deuterium or helium or something like that. So it bumps into a charged particle, and the charged particle scatters it off in a different direction. And this happens, I don't know, countless times per second. I can't even think about how to estimate that right now. Okay. So finally, at the edge of the convection zone, after about 1 million years of interaction and bumping around, the temperature has cooled. So here it's maybe like 1 million degrees or so, 1 million degrees Kelvin. At the edge of the radiation zone and the start of the convection zone, this thing has cooled down to about 1 million degrees Kelvin. Still, you can't have neutral atoms. Like, we're not talking about hydrogen atoms. We're talking about a sea of protons and electrons. And then at this point, things cool down enough where you can actually get things like convection and net flow of fluid. So you get these currents that set up in the same way that our atmosphere does it. So the outer edge of the so-called convection zone, for obvious reasons, is rather cool, 5,800 degrees. The inner edge of the convection zone is about 1 million degrees. So the hot gas, plasma, rises, cools down, and then sinks again. And these are set up in actually fairly stable patterns. So the convection zone is where bulk material is transporting instead of this like random jostling of radiated material. So if you look at the sun and you see sunspots or you see some sort of disturbance, odds are it's originating in the convection zone. So some like bulk flow of fluid is causing this disturbance. So the far edge of the convection zone is 5,800 degrees Kelvin for our sun. This is very cool compared to 16 million. And it turns out, what we'll get into next week, is this is exactly why we see the sun the way that we do. If it were a different number, it would look very, very, very different. So these are some of these cells of gas, and the temperature gradients are so tremendous, right? 'Cause you're talking about 1 million degrees to 5,800 degrees, that the gas itself cools and expands by a tremendous amount. So these larger cells are the upwellings, and then there are these kind of cell membrane-looking things in between them, which are much smaller and much more condensed. And these things are constantly bubbling up and cooling and sinking down. Any guesses about how big one of these cells of material is in the convection zone? Continent? Yeah, I don't think it's unfair to say that you could drop Texas into one of them, I think. So these are really big. And they're semi-stable, which is pretty good. So these are actually a picture, sort of false color, but yeah, you just drop California into one of those to get a sense of how big they are. Okay, so you've got these cells bubbling up and going down, and when you look at the sun every day, of course, which you shouldn't do, you notice that it looks the same, but do you think that the sun's surface is actually very active? Yeah. So ours is active, and we have a nice crust on top of us. We just have a little bit of convecting molten rock beneath us, and that's enough to give us earthquakes and volcanic activity. So in fact, this is kind of like a seething, roiling surface. You just don't tend to see it in visible light. And there are things like sunquakes, and literally called sunquakes, and other disturbances. Yeah. Everything but volcanoes, because what a volcano is liquid stuff punching through a solid surface, and there's no solid. But everything that there's an analog of on Earth, aside from that, there's an analog on the sun. There are sunquakes, and the sun actually is ringing like a bell. It actually has so much wobble to it that it set up standing waves, almost like a musical instrument. They're very regular, and you can decompose them into like known frequencies and stuff like that. So here's a picture of a sunquake. Bloop. And I know, I think so. There's no solid surface. You actually like see the stuff rippling out. So some crap bubbled up that was really hot, and the solar surface responded by having waves ripple out. This is not like a real picture. This is a depiction. So the red stuff is going away from you, and the blue stuff is going towards you. I don't know if you've ever seen some of these pictures of like a musical instrument where they show you how it's vibrating, and they're all very regular modes. The sun is absolutely doing that. And this is one of the higher modes. The lowest one would be like sun kind of going like front, back, front, back. And it's weird. There's almost like, they show up in regular frequencies. So it's almost, again, like a musical instrument. Yeah. How people actually know. So this is just like scientific artistry where they're painting they're just kind of showing you a representation of what's going on. How they know for real is through something that we'll really need to know later in the course, Doppler shift. So you can actually look at the light from a little patch of the sun and see if it's coming towards you or away from you. And Doppler shift is a really, really, really sensitive technique. Solar flares, like individually, are not necessarily predictable, but solar weather actually has kind of a cycle to it, which we're just about to get to. So nobody really knows if like a giant flare is going off, but you can kind of say like, oh, it's a bad solar flare season or something like that. It's kind of like weather on Earth. Is by the time you predict it, it's tomorrow. So yes, doesn't really look like it when you look at it, but it's very true. So most of that's set up in the convection zone just through these circumvecting currents. And then we get to the what collectively you could call the solar atmosphere. And at this point, the radiation and the heat and the material has fought its way to the edge, and now it's free to go and it zooms off. So the photosphere is the surface of last scattering, which is the same temperature as the edge of the convection zone. When we talk about the color of the sun and we talk about the temperature of the sun, and later when we talk about the color of a star and the temperature of a star, we're not talking about the core or the radiation zone or the convection zone. We're always talking about the photosphere, because that's the outer edge of this thing before something kind of weird is about to happen. So when people say sun is 5,800 degrees, they're saying this part, the photosphere, which is actually kind of almost like a onion skin layer, it's very, very thin, is the part that you see. And something kind of wild happens, which is still not completely understood, is the material heats up again. So you go from 5,800 degrees to almost 1,000,000 again at some point in the corona. So out here, there's something about the entropy and energy of, I made it to the edge of the sun, and now I'm just zapped off, and the solar wind actually heats back up to 1,000,000 degrees, which is kind of bizarre, but it's true. But we won't talk too much about that, because it's like, I don't know. There's some ideas about why, but the most important thing is that the part that you see, which, again, don't look at the sun, is the photosphere, and that's what we talk about when we say the temperature and the color of a star. It's nothing else. So, any questions about that stuff, actually, I could possibly answer? Not really a stellar astrophysicist. Our core is made out of protons. So you could think about it as hydrogen, deuterium, and helium, but there are no neutral atoms. So it's so hot that the electrons are free and the protons are free. But it's mostly hydrogen. Over the course of the sun's life, as this is happening more and more and more and more, so 3 billion years ago, it was mostly just protons. And this has been happening for about 4 or 5 billion years. So you get more and more helium. So this mixture, there's more helium, less hydrogen and deuterium in the core. Can you wait for 2 weeks? Because there's a really long answer which is central to everything that we're talking about in this course to that question. But you're absolutely correct. So the sun is eventually going to run out of hydrogen in its core, and it's going to have this basically like super balloon, so this giant blob of hydrogen sitting there, helium. And the question is, what on earth is it going to do next? And ours, because we actually live around a low-mass star, we won't go supernova. We'll do something else. And we will find a way to keep going past the helium stage. Unfortunately, the sun itself will puff up, and the edge of it will be about 1 AU in diameter. So when it turns into a helium-burning star, it'll also turn into a Earth-scorching star. That'll happen in 4 billion years, so you're fine. But yeah, there's a long answer to what happens to each individual star at the end of its life. They come in 2 flavors. There are supernova stars, which actually isn't one of ours, and then just normal red giant stars, which are the low-mass ones. So.
I don't remember what it's called. Solar system. Sorry.
Yes.
And we said that so all the celestial bodies are the same.
Yes.
I don't remember if the sun was included. So was the sun formed?
Yep.
Also when all that was?
Yep. 5 billion years ago. Yeah. Yep. And now that that's fresh in your mind, I can probably pick on you to answer this question. So when this big cloud of gas spun out and spread out into a disk like pizza dough style, do you think the sun that formed in the center of it is rotating?
That has to be fine, just like everything else.
Yeah. I think it's kind of fast.
Yes, I'd say faster.
Yeah. So remember that it's huge. So you can put 100 Earths across the sun. So fast is a relative thing, and at the edge of this, it's actually spinning 25 days per rotation. So the equator of the sun, if you were to, I don't know how you would do it, you would drop a little boat in the plasma at the edge of the convection zone, and the boat would ride around the sun at its equator, and 25 days later you'd see the little metal boat that you made at the edge of that. Okay. Yes. Like spinning a basketball on your finger, kind of rotating like that. And it's all in the same direction as the planet's orbit and the planet's spin. So here's something, so the sun's not solid, and it turns out that the fact that it's got a thermonuclear generator at the center and it's rotating guarantees that, in fact, it can't be all rotating at the same rate. So it's liquid. It doesn't have a solid surface. So in fact, the rotation rate at the poles is different, and it's 5 days longer to get the poles spinning. So in fact, the equator is spinning faster than the poles, which is a little bit weird, which seems like kind of a random piece of astronomy trivia, but it turns out that this completely explains sunspot cycles. So what? Well, we'll get back to that in a second. But the sun is spinning, It's very big, and it's spinning once every month or so. But remember, it's 100 times larger radius than Earth, so that 25 factor is actually really appreciable. So, it's also a giant ball of plasma. Plasma means that electrons and nuclei do not have to hang out with each other, so their charges are free to move. So I have a giant ball of spinning material in which electrons are free to move. What else do you think I have? So in the center of the Earth, we have a little bit of liquid metal that's convecting, and we spin once a day. Therefore, we get the aurora borealis. In Jupiter, you've got a whole bunch of this metallic hydrogen stuff, and Jupiter spins once every 10 hours. So Jupiter has this disturbingly big magnetosphere. Saturn's is big enough to melt Enceladus, apparently. So what do you think the Sun has? Yeah, the Sun's got magnetic fields, and the Sun has basically 2 to the 30th kilograms of ionized material, and it's spinning very fast. So I should have included this earlier, but this is a picture of plasma. It's like the same stuff, except in a neutral atom, the proton or nucleus and electrons are hanging out together in a bound stable unit. In a plasma, they're all free to go wherever. So the Sun has an absolutely outrageously big magnetic field. And the Sun has this really bizarre quirk of its rotation, is that the poles and the equator are actually spinning at different rates. So what ends up happening is, maybe you've all seen this. The pictures obviously can't show the whole thing, but magnetic fields don't have a beginning and an end. They're always required to be closed loops. Like, have you ever seen like a bar magnet and they trace the magnetic fields? They always loop around. And that's not like some weird piece of like mathematics pedantry. It's actually really required. So there's a very deep law of nature that says you absolutely can't break magnetic fields apart. So this is a problem because the Sun spins faster at its equator than at its poles. So these magnetic fields that would like to follow the plasma actually end up getting twisted. So over the course of, it's about 20% faster so at the equator than the poles. So once every 5 rotations, there ends up being like a full winding of the fields. So imagine doing this. You have like a rubber band, no beginning, no end, and you start spinning it around. At some point, the rubber band gets like really, really, really tangled. And at some point, the Sun starts freaking out about this. And this happens really periodically. And if you look at solar activity in the form of sunspots, you actually see this periodic freaking out. And it's about an 11-year cycle. So this is records of sunspot observations over the course of about a century or so. This is a really old chart. But the big upswing was in 2012, the last one, and people thought that, I don't know, it kind of fell by the wayside, but this like Mayan calendar end thing. You guys remember that? Yeah, so some people were like, of course, it's during the next upswing in the sunspot cycle. I think it was just because people got tired of chiseling shit into stone and said, let's end our calendar here. What do I know? So if you actually look at them, these are the sunspots in solar latitude. So this would be at the pole and this would be at the equator. There's also some pattern and some order there, and there seem to be matched pairs of them, which is really interesting, this kind of butterfly pattern. So when you look at a picture of the Sun, don't look at the Sun, what do you kind of notice about the sunspots? So you really kind of get in to there, to there, to there, to there, to there. They kind of appear in pairs. What's required by the topology of something is that they need to appear in pairs. I don't know if anybody's ever had to change in public or something, and if you want to take off your underpants without taking off your pants, there needs to be like a full loop of it. So you need to see like 2 ends of fabric coming out. And this is exactly what's happening as the Sun is trying to untangle its magnetic fields. So it can't cut through the loop. It's got to actually like unwind this thing and push it around and bulge it out. So in fact, these sunspots, these things you see, are actually 2 ends of some magnetic fields that have been like kind of pushed out and herniated by the Sun as it's trying to like untangle itself. So these sunspots, actually, they're more ordered, so the temperature is lower. They're almost 1,000 degrees on average lower than the ambient temperature of the sun, which is why they appear dark. But this, if you were to look straight on, you would see two dark spots. What's actually going on is this large loop of magnetic flare surface coming out. And this tends to happen in these kind of large sweeps of activity, peaking once every 11 years or so after like the sun gets all tangled up. It basically gets to breaking point and says, it's time to untangle, and then I'll tangle again. Okay, so do you see the pairs of them now? Yeah, now that you kind of know what to look for. But it's really true. It's like they do occur in pairs, and they are represented by this huge loop of magnetic field. So remember that you can put about 100 Earths across the sun. So how big are these arches of magnetic material? They're actually pretty tremendous. Yes, you could fly a couple of Earths through this, usually. So these are also associated with stuff being flung off the Earth's surface. And the first real strong evidence, and hopefully we don't have another one like this, that material was flung off of the sun's surface was a so-called Carrington event, where this observer, get his first name Carrington, was observing the sun, and he saw this, like a set of sunspots that had never been recorded before, like absolutely outrageous solar activity, like complete freak out. And he was marking them, and then recorded his observations, and about 3 days later, so it would take about 3 days at really high speed to get this material that flew off of the sun's surface to Earth. All of a sudden, all sorts of weird phenomena started being recorded. So the northern lights were visible in Cuba. Gold miners in Colorado woke up in their tents and went to work at 2 a.m. because it was so bright in the middle of the night that they thought it was dawn. So there was one evidence that like a telegraph was being able to, they could operate it without plugging the battery in. It was just kind of freaking out. There's so much electromagnetic radiation and plasma in the atmosphere. And some estimate is that if there was a Carrington event, a cosmic mass, corona mass ejection is what they call it, if it happened now, because we do all this communicating by satellites and stuff like that, it would be trillions of dollars of damage. So there are ways of classifying them. There are like solar flares of M class and X class. And if you go to spaceweather.com, no joke, you can actually like see what the sun's doing on this particular day. And there are some action plans if one of these things is headed right to hit Earth, right on the nose, to shut down power grids and to basically go into emergency mode. So
What would happen?
if something like this, communication satellites would be fried. A lot of power grids, if they weren't shut off, they would be fried, even if they were shut off potentially. It would be the equivalent of, the semi-sci-fi thing of the electromagnetic pulse, where people set off nuclear bombs in the upper atmosphere to zap all our cell phones and wipe all our hard drives. It would be that, actually worse, in fact. So now the flip side and the bad side of the grapefruit model is that if the grapefruit throws a temper tantrum and shoots off a stream of highly charged plasma, how big is the thing that's standing in the way of it? Crap, You'd have to be lucky to hit, but if one of these things like bopped Earth right on the nose, it would be trouble. So, bummer. So they're really pretty, though. So this is just some gratuitous pictures of what? I just looked at that. Crazy. Okay. It's a good thing I have many. It's also kind of where we're going in the future, is that this is obviously not what you see when you look at the sun. So this is not visible light. And the sun does not look particularly interesting in visible light, but in other wavelengths very much so. So I think this one and the next one, it's the same time scale. This is about a second is about 6 minutes or 5 minutes or so, I think. So this is a different wavelength of light, and it's paint by numbers. It's not really what the sun looks like. This is very, very short ultraviolet. And yeah, the NASA Goddard site, the Solar Dynamics Observatory, they put out all sorts of this stuff. They're so good at making these really slick movies. So this is actually much faster. This is about 5 years of solar data, and then they're going to switch wavelengths. So you're looking at a different type of non-visible light. And the nice thing about this is 5 years is enough to start seeing a full cycle of the solar storm cycle. So you'll see the sun starting to get angrier. And that's visible light. So exciting. Okay, but you see them, pairs of sunspots. I'm teasing visible light. Visible light knows I love it. Yeah, this would be, so we made it about halfway through, so that was about 2.5 years of solar activity. SDO is, everybody should subscribe to the NASA Goddard. So I think this is the one that, yeah, this isn't even a huge flare. I think this is the one that got blocked because I wasn't actually going directly to Goddard. And this is, again, I think it's the same thing. This is about 5 or 6 minutes every second. So they do develop pretty quickly. One of these has Earth to scale, but basically you could fly 2 or 3 Earths through that, through the loop. Okay, this one has Earth to scale. And you can fly 2 or 3 Earths through the loop. Remember, this is about an hour every 10 seconds, an hour of sun time. What's that? Yeah, it's they chose to paint everything this color, actually. So this is all ultraviolet radiation. This whole thing would be about 2 days, I guess, what we just watched. Yeah. So pretty fast, actually. Okay. So obviously there's something going on that needs to be explained in these pictures because, again, you absolutely don't look at the sun and see that sort of stuff, right? So now is the point. We've made it as far as we can before we can, without talking about non-visible light. And what really happened is the SDO, the Solar Dynamics Observatory, has 3 different cameras. You can make a camera that absorbs different types of light than the human eye. So the human eye is not special and visible light is not special. And SDO has, yes, a visible light camera, but then it's also got 3 different ultraviolet cameras. We only see visible light, so you've got to paint the visible light some color, like paint by number style. And astronomy is, from here on out, got to do that with everything, because we're going to squeeze the lemon and get all of the possible information out of every possible wavelength of light that we honestly can. Right? Yeah.
So,
So
looks the same.
what the SDO telescope is it's a observatory, so it's a satellite that's just kind of orbiting the thing.
Okay.
And yeah, it's honestly like it's a giant mechanical eye, and the ultraviolet light comes and it hits the back of a detector, which is made out of some really fancy chemical composition of like gallium arsenide or something like that. And it records photons, and then it tells us back on Earth how many photons hit this pixel. And then if more photons hit the pixel, we make it a brighter blue. And if fewer hit, it's a darker blue. But people don't really do science with that. They just like look at the photon counts. They just happen to be photons of a certain type, packets of light of a certain type. Okay. So because we have this human eye chauvinism, it's worth just being like very explicit about this, is that this is what's the same about light, and it's very good that this happens, is that all electromagnetic radiation moves the same speed in vacuum. So that isn't really required, and some things are kind of dispersive. But if a star does something wild and it emits like some radio waves and some visible light and some ultraviolet light, that all travels at the speed of light. That's about 300,000 kilometers per second, or 3 with 8 zeros behind it meters every second. It's very fast. That's the c in the speed of light squared and equals mc squared. So this thing gets squared to make a huge number. This is the same thing that we've been using all quarter with a light year. So, about 9 trillion kilometers per year. That's a light year. That's how long all light, no matter if it's ultraviolet or infrared or radio or visible, travels in a year. To put this in perspective, the moon's about 1.1 light seconds away. So if you've ever heard the entire footage of people landing on the moon and they're having the conversation with Houston, it seems something is kind of off about that conversation with this like really non-conversational conversation. It's like astronaut will say something. Yeah, it's absolutely the lag, because light, that is to say the radio waves that they're using to communicate, takes a second to get there, 1.1 seconds. So it's not that like Neil Armstrong was sitting there like, crap, what should I say? Everybody's listening. It's actually responding as soon as he heard, but it just took 1 second to get there, 1 second to get back. So the conversation sounded a bit delayed. Yep, a little bit of a satellite delay. Yeah. And then this is also means that every time you look at the moon, you're actually looking at it a second out of date. So if the moon blew up, you would only know 1 second later. Okay, so the light's about 8 minutes away. If the light did blow up, the sun did blow up, it would take us 8 minutes to figure it out. So we'd see 8 minutes of delayed light of totally normal sun even after the event. This starts getting serious because now we send probes to these things. When our orbits are aligned, Jupiter's about 35 light minutes away. When they're unaligned, it's about 50. So if you want to hear from your Jupiter probe, you got to wait like 50 minutes. If you want to have a conversation with it, it's about 2 hours. If you want to send something to Europa, you absolutely cannot remote control it, because you send an instruction and 2 hours later it does what you want it to do. Like, that's no good. So they do need to be autonomous. Voyager, this thing that we're managing to get out to the edge of our solar system, is now about 14 light hours away. So Voyager sends us a signal, 14 hours it gets to us. But if you looked at any part of light, it would totally look identical. This is just a cheesy picture that I compressed. Is that they're all wiggling electromagnetic fields. The wiggling electric field makes the magnetic field. So they all have the same speed of light. They all have the same fundamental description. The only difference in between light, any type of light, is the wavelength. So how close the peaks in the electric field are. And this can be a remarkably different amount of spacing. So the laws of electromagnetism don't care about what we see. We just have all of this like biological stuff that paints this on the back of our brains for some reason. But gamma rays, X-rays, ultraviolet, visible, infrared, microwave radio, they're fundamentally all the same thing. They all move at the speed of light through vacuum. It's just we put these kind of arbitrary distinctions on them based on how we as humans use them. Laws of physics absolutely don't distinguish in between them. They're all electromagnetic phenomenon. And to put some numbers on it, gamma rays can be as short as millionth of a billionth of a meter. It's very small. And radio waves can be meters. So the largest radio waves that we detect on Earth are like hundreds of meters across, tens of meters across. And if anybody ever stops you and starts babbling about how the human eye is perfect, just remind them that we see 1/2 of 1 order of magnitude of the 18 orders of magnitude that all visible light seems to span. So that's terrible. So we see 790 billionths of a meter to about 4.5 billionths of a meter. So we got all the astronomy that we can get out of this tiny little branch, and now it's time for that stuff. Okay. So the last warning, and this is what this is. So these are infrared and X-ray images. Sorry, ultraviolet and X-ray images. And from here on out, so there's Jupiter in infrared. We saw that before. It basically represents heat. Is if I don't tell you, you should ask, because all astronomy imagery has become false coloring. So this is ultraviolet imagery. This is, I think, the Chandra. So this is an X-ray image, and somebody had to paint this wonderful pastel thing on top of the X-rays. So if I don't immediately tell you, you got to be like, what part of the electromagnetic spectrum is that? And what we have left to do on Wednesday is talk about what different parts of the electromagnetic spectrum mean. So that's our goal for all of next week, actually. So I'll just leave that as a summary. Go. Okay. Good. Questions?